Yesterday's lesson was just a very basic introduction to this final collection of material that we're learning about modern physics, or the standard model of matter, which we're going to get into today. We started off by talking about the fact that if you want to break things apart, if you want to break matter apart at the nuclear level, then it's going to require high energy, so you need to use particle accelerators. Those particle accelerators operate in the millions and billions and even trillions of electron volts of energy, and that's necessary because the strong nuclear force that's holding things together at that level, or that deepness to matter, that strong nuclear force is large, so you need to really smash them together with a lot of energy to break apart things. We then talked about the fact that if you break things apart and you discover new particles, you have to have a way of seeing them, and we see them indirectly through the tracks that they leave in cloud chambers and bubble chambers. We also talked yesterday about the fact that you can apply the physics that you've learned of electric and magnetic forces and fields to those tracks. And we also talked about two processes that connect matter and energy. One was matter-antimatter annihilation, and one was pair production. In answer to, I think, Will asked yesterday, and I don't know if it was a question that was asked in front of the whole class or we had a conversation later, I can't remember, but the question was put forward, does the matter and the antimatter have to be the same type of matter-antimatter pair? In other words, we know that matter-antimatter annihilation occurs with an electron and a positron. And his question was, would it happen with an electron and an antiproton? And the answer is no. They have to be identical mirrors of each other except for the anti part. There's probably an exception to that, but we're going to learn about something today, and I'll be able to point at it and say, see, if antimatter and matter annihilated in this case, we couldn't have this particle, and we'll talk about that later, but they have to be the same. So there were a number of questions here. Does anybody have any questions from any of these that you would like me to explain or discuss or go over? Ian?
Could you explain the 4 and 5 of the chambers again?
Sure. Basically, both of these, let me just write them down first. Both of these operate on the principle of a change of state. You know, we talk about states of matter, solid, liquid, gas. There's that plasma state as well, but I'm not going to worry about that. They operate on the principle of changing state. And what a bubble chamber ends up doing is changing a state from a liquid to a gas. So what a bubble chamber has is I think it's sometimes called a superheated liquid. It's a liquid that's almost at the boiling point or the vaporization point. On the other hand, what a cloud chamber uses is the principle of going from a gas to a liquid. And the bubble chamber has a superheated liquid. The cloud chamber has a supercooled gas. You know, and when I say supercooled gas, you know, I don't mean it's ice cold necessarily, although you usually use dry ice to cool the gas down enough. And the point is that when you look at temperature and you look at states of matter, if this is temperature, we've got liquid here and we have gas here. So a cloud chamber operates at this temperature. A bubble chamber, I hope this is, I never explained it this way before, I hope this is making sense. A bubble chamber has a liquid in it that's almost a gas, and a cloud chamber has a gas in it that's almost a liquid. Does that make sense? And it turns out that if you agitate matter, when it's at that transition between one state and another, it can very easily change states. And you might think that's a little weird that if you agitate the gas, it can turn into a liquid, but if you agitate the liquid, it can turn into a gas, but that's the property of states of change. That's a property of states of change. So the agitation or the upsetting of the molecules or atoms that form these states is caused by that charged particle passing through. So when a charged particle passes through a cloud chamber, it turns the gas that it interacts with into a liquid, and it leaves a trail of little liquid particles in the cloud. It's like a contrail from a jet. Okay, it looks like that. It's not like that, I guess I shouldn't say, because a contrail from a jet isn't necessarily liquid. It's just a different color gas. When a charged particle goes through the liquid, it vaporizes the liquid, turning the liquid that it's running into gas, into bubbles. So you end up with a trail here of bubbles, which is why it's called the bubble chamber. Okay. Am I getting to the heart of your question?
Well, I was wondering, that number 5 says list 2 subatomic particles that will leave tracks, and so I'm thinking, well, does that mean that charges affect which one will create bubbles in one chamber and the other?
Okay, so first of all, and I don't know, this might solve the problem that you're having. The answer to number 4 has nothing to do with the answer to number 5. Nothing. It isn't that bubble chambers detect one type of particle and cloud chambers detect another type of particle. Both cloud chambers and bubble chambers will only ever detect charged particles. So when you're asked, and this is, I don't even know that I want to get into a reason for this because quite frankly, I don't know the exact reason. But the fact of the matter is you need to know that these chambers, these detection devices that we've built, only detect particles with charge. So what are some subatomic particles that would leave tracks in a bubble chamber? Well, an electron, because an electron has charge, a proton, a positron. Rare as they are charged and they are subatomic. What are some subatomic particles that will not leave tracks? Neutrino, antineutrino, they have no charge. Neutron has no charge. I think in the answer there, and I pulled the answers from the textbook with a bit of editing, it says a gamma ray, a photon. I don't really care for that answer because I don't consider a photon a subatomic particle. I think a photon is in its own class. It's not a subatomic particle. Other questions? Will?
How do you detect a particle that doesn't have a charge?
I don't want to answer that until I'm sure I know the answer. The question is, well, how do you detect neutrons? How do you detect neutrinos? And I have an idea, but I don't want to say in case it's wrong. So let me check that out and we'll find out. Yeah. But it does bring up an interesting question, is there have to be other detection devices? Because if we use this whole particle accelerator combined with detection devices to discover new particles, how did we discover, how did we actually see evidence for a neutrino or an antineutrino, which has no charge? However it was, I'll leave it here for now, it wasn't with a bubble chamber or a cloud chamber. Okay. Other questions? All right, so this is it. This is the final set of ideas we're going to be talking about and learning in this unit, which means in this course. And this lesson is based, the title of this lesson is based on what your textbook has for this section, which is Models of Matter Continue to Develop. So when we talk in the bulk of this unit about the electron structure and different models of the atom, and then we go to the nuclear structure and all these forms of decay and fission and fusion, that's not the end of the story. That's why this is called what it's called. So we're going to be talking here about the standard model of matter in very Simplistic terms, it gets quite complicated. You're going to discover that a lot of what we do today is about memorization. You're going to have to know names of certain particles and names of types of particles. Some of those particles happen to be called fermions, and we'll get to that in a bit. We're going to explain forces in terms of mediating particles. Nobody has ever asked in this class, why is there an electric force between two charged particles? Nobody's asked that, right? Why is an electron attracted to a proton? And if you were to ask me up to now, I would just say, well, because they're oppositely charged and opposite charges attract. But that doesn't really tell you why it happens. There is an explanation in the Standard Model of Matter as to why it happens, and it has to do with something called mediating particles. And then we're going to try to connect what we learned today about something called quarks to beta decay and positron decay, and we could even apply it to electron capture. So to begin with, quantum field theory, which is a subset of the Standard Model of Matter, it's a theory in physics that helps to support the Standard Model of Matter. And again, every time I use the word theory in high school, I feel the need to tell you, it's not some, the theory. It's not some hypothesis. It's a theory. A scientific theory is something that is based on evidence. It's a fact. Explains the four fundamental forces in terms of these things called mediating particles. Now, a mediator, if you had a labor dispute between an employer and a union of employees, they often get a mediator to bring them together. So a mediating particle is a particle that produces the force that connects, that connects these particles together through a force. And these mediating particles are sometimes called virtual particles because they only exist for a very short period of time. They only exist to produce the force. But they're always existing, and what I mean by that is they appear and they disappear and they appear and they disappear. And this actually happens. There are these particles that are doing this to explain the forces. So this is the table of the four fundamental forces, and your table is completed. You don't need to fill anything in. We're on page 52. Okay, we're on page 52. So to review, these are the four fundamental forces: gravitational, weak nuclear, electromagnetic, strong nuclear, in the order from weakest to strongest, at nuclear distances. When you compare gravitational and the weak nuclear, there's this huge gap in terms of strength. Gravity is just such a weakling among these four forces. But then as soon as you get past the weak nuclear into the electromagnetic, I believe this is 10 to the 36. So it's 10,000 times greater, which is a big leap as well, but saying the electromagnetic is 10,000 times greater than the weak nuclear is nothing compared to saying the weak nuclear is 10 to the 32 times greater than gravitational. And the strong nuclear is about another 100 times greater than the electromagnetic. We've learned this before. We've learned that as far as physicists believe now, their theories say that electromagnetic and gravitational forces act over infinite distances, whereas the strong nuclear force, and I hope you remember this number, has to be within a femtometer because that's a nuclear distance. And if you're not within that femtometer, this strong nuclear force, which holds all of the protons and neutrons together in this clump of matter, that strong nuclear force would not exist. The weak nuclear force exists deeper. I don't know that you need to remember this precise number, but since the weak nuclear force is responsible for beta decay, and beta decay happens inside of a neutron, that's deeper. That's further in. And then you also have, if you were to assign 1 the strong nuclear, all of these exponents get flipped over and become negative. Okay. And there's nothing new there. So let's start with electromagnetic. What is the mediating particle that produces electric forces and magnetic forces? It turns out it's the photon. it's a photon. We don't want to classify this on the electromagnetic spectrum because that's not what's important here. We have actually observed this. So when you have, there are a number of different experiments that detect these photons. When you have a charged sphere next to a charged sphere and they are pulled together or repelled, when you look in the space between them, they are firing photons back and forth at each other. This is just an analogy, and most analogies at this level in physics totally break down. You can poke holes in them easily. But it's like two people standing on ice throwing a big medicine ball back and forth. And every time one person catches it, they're pushed a little bit further away. And every time that person throws it back, they're pushed further away. And every time the other person catches it or throws it, they're pushed further away. So these photons are being exchanged by the two charges to push them away or pull them together. The analogy doesn't work in trying to explain why they come together, why opposite charges attract, but we have observed that. The strong nuclear force, now I often call the nuclear force the nuclear glue, and I may have used that before. The strong nuclear force, these are called gluons, okay? And we have detected them indirectly. Experiments continue to improve. We haven't seen them directly, but we have done experiments that really, really lead us to believe that, well, no, there's that particle is there, something is there. And by the way, I know you know this, but it's not like if you could see it, it would say gluon on it. That's just a word we give to the particle. The weak nuclear force, there are three. Now, you don't need to remember which one is responsible for which, and quite frankly, I don't remember them. I'd have to work it out. But you have the W bosons and a Z boson. And the weak nuclear force is responsible for beta decay, positron decay, and electron capture, basically. Any change where a neutron changes to a proton or a proton changes to a neutron is one of these three particles. And we have observed that. And these particles so far, these gluons, photons, and the W positive and negative and Z, what we call bosons, and I'll get to that word in a second. Sounds like the name of a clown, but they're called bosons. They exist for like nanoseconds, really, really tiny periods of time. The hypothesized particle to explain gravity is called the graviton, and it has not been observed. And I'm going to say this once, maybe I'll say it again later, but I probably will not. Even though in physics in high school we say that the standard model of matter has 4 forces, quantum physicists don't believe gravity is one of them. They actually believe there's 3 forces, and they explain gravity in a totally different way. Okay? So if you were to do some research online, you'd find charts and diagrams showing the standard model of matter, and it's got electromagnetic and weak nuclear and strong nuclear, and then over here in a different room is gravity. Gravity doesn't seem to fit in here. It's explained in a different way. But in high school, we talk about this. Okay? Briefly, any questions about these charts or particles? Yes?
Do any of those particles have masses?
Do any of these particles have masses? Well, we can't say about the graviton because we haven't detected it yet. I would say well, photons do not. I don't believe gluons do, and I don't believe the W and Z bosons do. So I'm going to say no. If they have masses, they are too small, so small that we have never detected them as having masses. The other issue I have is, and I don't know, I'm really being honest with you here, we know about photons. We know what they are. They're massless particles. They have energy, which means they behave like mass, but they don't have mass. Well, I'll just show this to you. These are all called bosons. Okay, let's get that out of the way. It's the only reason why we say W boson and W boson and Z boson is because it's a nice way to describe them rather than saying W minus, W plus, Z zero. But these are all bosons. remember, the bosons only exist for really, really tiny periods of time, nanoseconds. So I'm not sure how you could detect whether they have mass or not. Part of me wants to change my mind here and say the charged bosons must have mass. But I'm going to have to do research. So I've got a couple of things that you've asked today that I have to look into. Ian?
Will you have enough time to describe the process of what goes into experimenting to find out that these particles exist?
No. And even if I did, I would probably be, to be honest, I would probably be bluffing my way through it because I don't know the precise details. You know, this is that story of me buying that textbook on the Standard Model and trying to teach myself all of this, and it's just way beyond me. And it is why, we need to remember, it is why this is just a cursory exploration of the Standard Model of matter in Physics 30. All right, so the Standard Model of matter explains the behavior of all matter in terms of these mediating particles and about 300 other particles. And I put the word fundamental there, and your textbook uses the word fundamental here. I don't want to use that word fundamental, so I think you should cross it off. Fundamental seems to imply it's not made of anything. And in a while, I'm going to tell you that all of the stuff in our universe, like all of the physical stuff that has heft and mass and behaves certain ways, not the mediating particles and the forces, but the stuff that the mediating particles act on, is made up of only 24 fundamental particles. That's it. So that's a lot more than proton, neutron, and electron, which we thought were fundamental, say, 50 years ago. But there's only 24 truly fundamental particles. So you've been told up till now that protons, neutrons, and electrons are fundamental, which means non-divisible. But it turns out that the proton has parts to it and the neutron has parts to it. Okay? So it's like Dalton believing that an atom was indivisible. Well, we've discovered the atom has parts, a nucleus and electrons, or a positive stuff and electrons. Then we discovered that positive stuff has parts, protons and neutrons. Now we're going deeper and we know that protons and neutrons have parts. The electron is fundamental. You know, could we, somewhere down the road, could Physics 30 students 100 years from now being taught, oh, we used to think electrons were fundamental and now they're made of something? Maybe, but right now we believe they're fundamental. Now, all matter, everything with substance, matter, is made up of particles called fermions, and you need to know that word. Okay? So fermions are sometimes called the building blocks of matter. If you could take this battery charger or my drill or this remote control or this jug of hand sanitizer and just keep tearing it into smaller and smaller pieces, sooner or later you would have a whole bunch of fermions. And fermions, there are two types. There are leptons and there are called quarks. And you need to know that. So you need to know that all matter is composed of stuff called fermions, and there's two types of fermions, leptons and quarks. I will tell you right now the fundamental difference between a lepton and a quark. Quarks get together with other quarks to form more complicated particles. Leptons exist on their own, basically. Okay. Two examples of leptons are what we call the electron. That's the same electron we've been talking about for years in school, in your education. An electron is a lepton. An electron is a fermion because leptons are fermions. So we have leptons. There's a class of leptons called, there's a class of fermions. We have fermions. There's a class of fermions called leptons, and one example of a lepton is an electron. There's also an electron neutrino, which is a lepton. So both of these things that I'm listing here, this electron and this electron neutrino, are examples of leptons. When we talk about the neutrino emitted during positron decay, that's the electron neutrino. Okay? When we talk about an antineutrino emitted during beta decay, that's an anti-electron neutrino. The neutrinos we've been talking about are called electron neutrinos. And because an electron neutrino has that extra label of electron, that tells you there's other types of neutrinos. Okay? There are other types of neutrinos. On the other hand, two examples of quarks are named the up quark and the down quark. These are just words that physicists use to label these particles. It doesn't mean there's something physically upwards about an up quark and something physically downwards. They just needed two words to describe them, so up and down. So if you were to look at kind of a flow chart, we have fermions. There's two classes of fermions, leptons. Two examples of leptons are electrons and their neutrinos. There are also quarks. Two examples of quarks are the up and down quark. But there are these two leptons and four more leptons, and these two quarks and four more quarks, right? So these are the fermions, and at any point during this lesson, if you want to take pictures of this, feel free. That's what we're talking about. So physicists use the word flavor to describe the type. Okay? What is the flavor of the lepton? Well, it's an electron. What is the flavor of that other one? It's an electron neutrino. And there are the charges. And right away you notice something. The charge on an up quark is 2/3 of an elementary charge. The charge of an up quark is not a multiple of the elementary charge. Why was Millikan never able to detect charges on oil drops with weird charges like this? Because he wasn't using anything that could tear apart nuclei and discover these individual charges. These up and down quarks get together to form +1 and -1 in a certain combination. These, by the way, are called the first generation fermions. There's a second generation of fermions. And there's a muon particle, which is a lepton, and its muon neutrino. That's the second generation of leptons. And then the tau and the tau neutrino. And then we have these other quarks, charm and strange, top and bottom. You were expected to know properties of the first generation, but not of the second or third generation. That being said, let's go to your formula sheet. I might as well show this to you now. Let's grab your formula sheet. And if you go over to the particle side, you see something there. It's a chart called first generation fermions. I don't want you to worry about the weird stuff under mass. I want you to notice that there's the electron there. There's the electron neutrino. There's the up quark. And there's the down quark. The up quark's charge is given to you. The down quark's charge is given to you. Also, as well as those four particles, the two leptons and the two quarks, are their four antiparticles. So the structure of this is it shows you a lepton that's an electron and then the antiparticle of it, which is a positron. The electron neutrino, which is a lepton, the anti-electron neutrino, which is the antiparticle. The up quark, this is goofy. It's not just called the anti-up quark, it's called the anti-up antiquark. To me, that's a double negative, and we're back at a quark, but that's the notation that they use in the language. And then the down and the anti-down. All right, hadrons. So here's another word. It's bold. You need to know what a hadron is. A hadron is what happens when quarks get together to form other particles. And hadrons, as far as we know, are always composed of either 3 quarks or 2 quarks. And you don't need to know the fact that if we have 3 quarks, it's called a baryon or an antibaryon. You don't need to know that, but those are the words. You don't need to know that if you have 2 quarks together, it's called a meson. But you do need to know that when you have 2 or 3 quarks together, the resulting particle is called a baryon. 2 very important baryons that you need to be intimately familiar with, baryons, but they're hadrons, are the proton and the neutron. You need to know this, and it's nowhere on your formula sheet, it doesn't tell you this, that a proton is a 3-quark combination of up, up, down. Now, I know it's up, up, down, probably because I've memorized it, but remember, an up quark is positive 2/3 of an elementary charge. A down quark, I'm just putting them up here because this is where I have room, is negative 1/3 elementary charge. So how can we get these 3 quarks together, 3 of these 2 quarks, so that we would have no charge, let's say? Well, since the down quark is only half the amount of negative charge that the up quark has positive charge, we would need 2 of those down quarks, wouldn't we? And if you take 2/3 and add 2 times negative 1/3, which means you have an up, down, down, you'll get nothing. The only way to get positive 1 is to have 2 of these up quarks, which gives you positive 4/3, and you take negative 1/3 and you add it to that, and you're left with 3/3. The antiproton, well, an antiproton would have an anti-up antiquark, an anti-up antiquark, and an anti-down antiquark. This is why the charge on an antiproton is negative 1, because all of the individual quarks that are inside of the proton have switched charges. They've changed. I don't know if you recall, but I told you a neutron and an antineutron are actually oppositely charged as well. It's because an antineutron, I think I have it here. Maybe I missed it. I might have it later on. An antineutron, I'm just going to write it here. It's not a meson. An antineutron has, let's see, neutron is up, down, down. This would be an antineutron. So all of the quarks are opposite, so all of the charge is opposite inside of the neutron, but when you look at the entire neutron, you don't see any charge. There's lambda hadrons and omega negative hadrons. So a lambda hadron is an up quark, a down quark, and a strange quark. And omega is 3 strange quarks together. The reason, and now I can get to Will's question from yesterday, the reason why it's very clear that the particles have to be the same and for matter and antimatter is because when you take a look at the mesons, they all contain, and there's other exceptions here because, for example, a charm and an anti-charm quark don't annihilate each other. But I know for a fact that when they're different types of particles, they will not annihilate each other, even though one is matter and one is antimatter. If I gave you on an exam, so you need to know the properties of the proton and neutron and the up and the down quarks. If I gave you this information on an exam, I told you the charge on the up and down quarks, the charm and strange quark, the top and the bottom quarks, you should be able to determine the charge of a hadron if I give you the structure of it. Okay, so for example, if I said, I think we had a hadron, I think it was the lambda hadron, was an up-down strange quark together, if I gave you this information, you should be able to determine the charge of that hadron. The up would be 2/3, plus the down would be negative 1/3, plus the strange is negative 1/3. The up-down strange quark combination would be neutral. And I don't know if you notice that this quark is going up, this quark is going down, this quark is trying to charm somebody. This is strange, clearly. This is a top quark, and this is a bottom quark. Okay. I know you know this. It's just a cartoon. Quarks don't look like that, right? It's just a visual thing that somebody has made up. This is kind of how I feel. Fermi, the discoverer of nuclear fission. If I could remember the names of all of these particles, I'd be a botanist. You are required to remember the names of some of them and some of the classifications, but not all of them. All right, let me catch up to where we were. By the way, there's about 120 baryons, 3-quark combination particles that we've discovered. There's about 140 mesons, 2-quark combinations. That adds up to 260. That's why earlier in your notes it said there are about 300 different particles. But there's really only 24. The 2 first-generation leptons and first-generation quarks gives you 4. The second generation gives you another 4. The third gives you another 4. That's 12. And then they're antiparticles. That's it. Once again, here's the first generation fermions and their antiparticles. So these are the leptons and these are the quarks. So just to run through, this might be helpful, and you can certainly take a picture of this when I get to the end of this slide. This might be helpful for you visual people. The Standard Model of Matter talks about bosons, which explain force, and fermions, which explain matter. Fermions are either leptons or quarks. The leptons you need to be familiar with are the electron, neutrino, and their antiparticles. The quarks that you need to be familiar with are the up and down quarks and their antiparticles. And when I say familiar with, you have the information on your data sheet. Quarks get together to produce hadrons, and then the 2 hadrons you need to be really familiar with is the structure of a proton and a neutron. And the bosons, of course, you need to know this. You need to know on an exam which boson is responsible for which force. It could be a numerical response question. It could be a multiple choice question. I'll leave that there for a second if you want to take a photo. And while I'm just waiting, does anybody have any questions before we move on? Okay. So, example. This is called example 4 because we did 1, 2, and 3 yesterday, and this is just a continuation. When you look at your formula sheet, at the mass of an electron, not in that other area, not up here where it says mass of an electron is 9.11 times 10 to the negative 31. When you look under the first generation fermions table, why is the mass of an electron given the way it's given? 0.511 million eV over c squared. Well, first of all, mass and energy are the same thing at this level of physics. So if you were to ask a nuclear physicist for the mass of an electron, they're likely to just say it's 0.511 million electron volts, and they won't even say over c squared. And the reason for that, and then we'll do the calculations, is if you take the mass of an electron in kilograms and convert it to energy, that's what you're going to get. But let's talk about the units here. If E equals mc squared, then mass is equal to the energy that that particle has divided by the speed of light squared. So we can express mass in terms of units of energy over the speed of light squared. Well, let's take and calculate that energy. Let's take E equals mc squared and calculate how many joules of energy is equivalent to the mass that an electron has. (9.11) multiplied by 10 to the negative 31, and then times the speed of light squared. That many joules. Do you get the same number? Okay, 8.199 times 10 to the negative 14. Joules. So now I have a question for you, and it's a silly question, but what would you do to that energy to find the mass? Divide by c squared. So again, I'm going back to the idea that the mass is the energy over c squared. But physicists don't like, especially nuclear physicists, don't like to use joules for energy. They like to use electron volts. So let's convert this to EV. And I get 512,000. I get 0.512 million EV. So if you wanted to convert this energy to the mass, you would have to take that energy and divide by the speed of light squared, which means this is how we could write the mass. Now, of course, you can't divide this number by the speed of light squared because the units are not compatible. But this is the meaning behind that number on your formula sheet. Now, we do have to address the fact that on your formula sheet it's 0.511, and here we're getting 0.512. That's because the mass on your formula sheet is not the true mass of an electron. There's more decimals to it. The speed of light is not actually 3 times 10 to the 8. It has more decimals to it. The number of joules per electron volt is not exactly 1.6 times 10 to the negative 19. If you were to use all of the digits we know about these measurements, this is what you would get for the mass of an electron. You'd get 0.510998, and it's rounded to 0.511. It's kind of like the incompatibility with Planck's constant when we do photon energy calculations. Sometimes you get a slightly different answer. B, what is the only difference between an up quark and its antiparticle, which is called the anti-up antiquark? What's the only difference? Well, look at your sheet. Look at the formula sheet. Charge, that's it. It's the only difference. The charge on an up quark is positive 2/3 elementary charges. By the way, that means that if you actually wanted to know the charge, and I don't know under what circumstances you would be asked that, but you could be, then you would take 2 divided by 3 times that number. Whereas the charge of an anti-up antiquark is negative 2/3 elementary charges, which means if you wanted to calculate that, that's how it would be done. It's the only difference. And now we get into the most important example. So any questions with 4a and b, or 5a and b rather? Yeah.
When we're calculating, when we're using the formula E equals mc squared to find mass or the energy corresponding to mass and the speed of light,
Okay.
why there. They're not moving at the speed of light. Why do we care about the speed of light in the formula?
Because what we're finding, the fact that they're not moving is not relevant. What we're finding, that energy in the E equals mc squared, is not their kinetic energy or something. It's the energy that they possess because they have mass. It's the energy they have. If we could convert all of their mass to pure energy, that would be the energy we get. And I would just leave it at this, that the reason why we want to talk about energy is conservation of energy is what's going on here. Okay? It's actually conservation of mass energy in nuclear changes, right? Energy is not conserved, but mass energy is. So when you have a nuclear change, if there's mass involved, physicists just change it to energy so everything can be energy. They're saying energy is conserved, and some of that energy is true energy, and some of that energy is mass that we're treating as energy. Is that?
Yes.
Okay. All right, so there's a diagram of a proton and a diagram of a neutron. By the way, there are different types of up quarks. Quarks have something called color charge. It's not charge, it's called color charge. And there are three types of color charge. Okay, red, blue, and green. So it just turns out that in a proton, you have two up quarks, and one of them has a red color charge and one of them has a blue color charge. But we don't need to worry about that. Color charge was invented to explain what's going on here. Okay. But you may see on an exam different colors. Here's a proton, there's a neutron. The question is, use the standard model of matter to explain what happens during beta decay. Okay, that's a pretty vague question. So we need an element. Jack, can you give me an atomic number greater than, say, 10? 13. So 13 is aluminum. It has 13 protons in the nucleus. So, Carly, can you give me a total number of protons and neutrons that this might have? If it's 13.
Like any number?
Whatever, yeah. Reasonable number. Don't say a million.
234.
Maybe too big.
112.
Still too big. Remember, yeah, okay, I'll go 87. I don't think there's an isotope of aluminum 87, okay? But that's okay, because what I'm trying to get across to you is you can make up anything you like. We could have gone with 200 and something, but I wanted it a little more realistic.
Sure.
If this is an isotope that we could manufacture in a lab, it would be incredibly short-lived, because the general rule is that top number is usually 2 or 3 times the bottom number. How many of you would agree to that? Okay. But we'll go with it, because what I'm getting at is you're writing an exam and you have to figure out what happens during beta decay, and that's it. You're not told anything. So we're going to look at the beta decay of this imaginary, I'm saying imaginary because we made it up, isotope of aluminum. Well, a beta particle is this. Of course, it's accompanied by, it's not a vector symbol, it's accompanied by an antineutrino, which is this, and now we can figure out what else is there. Well, the top number still needs to be 87. The bottom number needs to be 14 because we already have a -1 for a charge, and -1 plus 14 is 13, and that tells us that we get silicon 87. And again, this is very important you understand this. We just made this up. It doesn't matter whether it exists or not. It doesn't matter whether this happens or not. You're trying to figure out what happens during beta decay. Well, this equation here is an elementary type of explanation for what's happening. Okay? It's a very simple explanation. But we have learned that this means there's 13 protons and 74 neutrons. Yes? How's my math there? I think that's right, isn't it? Adds to 87. And this changes into Well, this is an electron, and you'll notice that I went away from the nuclear notation. I didn't write for the proton 1,1p. I just said there's that many protons, that many neutrons. I'll do the same thing here for the electron. I'll do the same thing here for the antineutrino. And then over here we have 14 protons and 83 neutrons. And again, just double check my subtraction there. I'm pretty sure that's 73. 73. Capiche? We've done this before. This is not new. And what we could do then is say, well, you know what then? What's really happened is this. What's really happened is this. The net effect is that a neutron has transformed into an electron, an antineutrino, and a proton. And we've done that before. And I would describe this as being elementary. And I don't mean elementary like elementary school. I mean it's a very basic approach. This is kind of an intermediate explanation as to what's going on. So when, you know, if you say, where does the electron come from, and you're looking at the Brown equation, you just kind of go, well, that's what beta decay is. If you say, where does the electron come from, and you're looking at the Green equation that I wrote, well, actually the red one, right? This whole thing goes together. I'm going to actually change this to green. No. Can I? Yeah. This whole thing is the intermediate explanation, right? But it culminates in that bottom line. But that's not very satisfying, or it's not as satisfying as it could be. It's no real explanation as to what happens to produce the electron. But what you can do now is use maybe an advanced description of what's going on. And a neutron is an up, down, down quark combination. And that changes to an electron, an antineutrino, and an up, up, down quark combination. And by the way, the total charge on this is 0, and the total charge on this is positive 1, correct? And if you look at the charges on the right, negative plus 0 plus positive gives you 0, charge is conserved. But inside of this neutron was an up quark, a down quark, and a down quark. Inside of the proton, there's still an up quark and there's still a down quark. But there's another down quark. So what's happened, sorry, there's one less down quark. There's an up quark. What's happened is this guy is still there. This is still there. But that other quark changed. That down quark, which has a charge, well, I'll get to the charge in a second, has changed to an electron, an antineutrino, and an up quark. And we can put the charges in. Down is negative 1/3. Up is positive 2/3. And if you add up the charge on the right, you're going to get negative 1/3. Charge is conserved. And that's a more satisfying explanation to say, well, what happens during beta decay? Oh, an electron is produced in the nucleus and is spit out. Okay, what does that mean? Well, it means a neutron changes to an electron, an antineutrino, and a proton. Well, what does that mean? It means that a quark has changed into these. And that's maybe not as satisfying as it could be, but the PhD level explanation here would involve me teaching you color charge, and we could have a whole lesson on color charge. It's really amazing. Because you know how when you mix colors of light, there are rules for colors of light? They use the phrase color charge because when you mix color charges, the same rules apply. Okay. So that's what happens during beta decay. Any questions with the process there that we went through? Okay, let's quickly run through one where it's positron decay. Use the standard model of matter to explain what happens during positron decay. Ian, can you give us an atomic number? 52. 52 is tellurium. Annalie, can you give us an atomic mass number that tellurium might have? 115. Okay, 115. You should know that positron decay would be this, using nuclear notation. And you should be able to figure out what we have left. This is nothing new again. Top number, which is nucleons, has to total 115. Bottom number, which is charge, has to total 52. So during the positron decay of tellurium 52, you get SB 115. I gotta rack my chemistry head for that. Is that antimony? Antimony 115. Very basic explanation for positron decay. Is my basic math right there? Okay. I'm not going to write down that this is a positive, well, I guess I could. This is a positive electron. This is a neutral neutrino. I said this is a neutral neutrino, as if there are other types of neutrinos. There aren't. It's a neutrino. Neutrinos are always neutral. And then over here, what do we have? We only have 51 protons, and we have one extra neutron. So the kind of intermediate explanation for what's going on here is a proton changes to a positron, a neutrino, and a neutron. And don't sell yourself short. That's a pretty deep explanation as to what happens during positron decay. But we can go deeper, because a proton is an up-up-down quark combination, which adds to give positive 1 for a charge. We have a positron, which has a charge of positive 1. We have the neutrino, which is neutral, the neutron, which is an up-down-down, with a total charge of 0. And again, everybody, don't forget, when I say that up, down, down is 0, that's only because the up quark is positive 2/3 and each down quark is negative 1/3. There are individual charges in here. But when you take a look at it, the only thing that's changed, the up and the down quarks in here are still there. The only thing that's changed is this. And again, not that it really matters, but when you take a look at the different colors of the quarks, it's because of the change in the color that changes the type of quark. So what actually happens is an up quark with a charge of positive 2/3 elementary charges turns to a positron with a charge of positive 1, a neutrino with a charge of 0, and a down quark with a charge of negative 1/3. And if you add up the charges on the right, positive 1 for the positron, plus 0 for the neutrino, plus negative 1/3 for the quark, you get positive 2/3, which is what the charge is on the other side. And you will see questions for sure on my exam where it's like, which of the following shows the quark transformation that occurs during beta decay? And you might even see a question that asks you for the intermediate understanding. During positron decay, what's the nucleon transformation? Protons turning to neutrons, neutrons turning to protons, what's happening? Any questions with that final example? Okay, so you have a series of questions attached to this. You guys can get started. I want to give you some time here to get started on this, so you have about 15 minutes left. But while you're working, if you're not interested, you can continue working. If you are interested, are there any other questions? Ian?